All right, so lesson one, the basics. If you don't understand how electricity actually works, then you're not going to get very far, as we talked about. And for everybody on YouTube, if you have questions, feel free to write them in the comments, and I'll answer them as I can. So the caveat that you need to know is I'm going to be going through pretty much an entire semester in about 30 minutes or less. So I'm going to maybe misspeak, or there's going to be things I gloss over. There may be things that you need to go research on your own if you don't understand it entirely, or if something kind of perks your interest. Feel free to go do it on your own. But I will be going very fast. I may misspeak. I will be glossing over a lot of stuff, but there's a lot more in depth. I'm just trying to get the concept down for mechanical people of electrical principles so that you can at least wrap your head around. It's not meant to be, I'm going to go take the test now. No, that's not how this is meant. It's just for, I can understand what my electrical counterparts are now talking about and provide helpful input. Hopefully that makes sense.
Sounds good.
Awesome. All right. So, structure of an atom. If you remember back in 5th grade, for me, this is what the atom looked like way back when. So you got protons, neutrons in the middle, and then you got electrons floating around. Positive and negative in the middle. I'm sorry, positive and neutral in the middle. And then you got the negative electrons floating around going very, very fast. Okay. If you can remember the electrons are on the outside and they're negative, that's going to help you in future conversations.
Okay.
Right. Valence electrons. All atoms have what are called valence electrons. You can only fit 2 in this first shell. You can only fit, was it 8 in the second shell, so on and so forth. There's a maximum number of electrons you can fit in each valence shell. And the quantity of valence electrons obviously influences where it's at on the periodic table and the ability to gain or lose. Because if you're slightly more negative on the outside and you only have 1, as in copper,
you can easily lose that one.
You can very easily lose it, yes. And the resistance of losing that we will come back to later, but that's the idea. How hard is it to get that electron off of that outer shell? All right, so the periodic table. Hoping this didn't freak out on me. Apparently it did. There we go. All right, so copper. You can see you got 1 valence electron on the outside. Same thing with silver, same thing with the gold. Technically, gold is the best and most practical, the best metal to use in like wiring and whatnot. But it's super expensive and super precious. Silver is the next best, but it's still super expensive. And that's why copper is the most common to be used next to aluminum. Okay. Copper and aluminum are the most common uses of wires or conductors or half a dozen other things in there. Now, we do also have zinc-coated bus bars, silver-coated bus bars, and nickel-coated bus bars for various reasons, especially in like the water wastewater industry where it's very corrosive, or industrial plants where they've got a lot of corrosion in the air. Cover everything with zinc, silver, because it doesn't really mess with the flow of electrons for the most part. All right. And if that doesn't make sense to you, just edit up that.
Okay.
All right. So if I have a magnetic wire, the magnet, and I've got a copper wire, right? And this is my positive side, and this is my negative side of the magnet, and I move this thing to this side, which way are my electrons flowing? To the right or to the left?
To the left. To left?
Are you saying that way?
Yeah.
So opposite attract, right?
Yeah.
So the electrons are actually flowing that way.
Okay. Oh, okay. I was thinking from the just the magnet's perspective. You're saying from the copper wire to the magnet is what you're saying. Yeah, that makes sense. Because the copper wire, the negative outside shell, like it will move to the magnet, going from like the negative to positive.
Yes.
Like that. Okay.
Yep. All right. So when I do that, and you make a very good point that I completely glossed over that you kind of need to know. Let's bring a copy of this. Thank you for bringing this to my attention. And I will be doing this on the fly, by the way, so.
All good. I figured everything's going to be on the fly. So.
Yeah. All right. So this copper wire that you see here, oh man, my thing doesn't work no more. Oh well. The copper wire you see here has a bunch of copper atoms in it because that's what it is, copper wire. So when I move the magnet this way, like this, those copper atoms don't actually move. The valence electrons move. So this one will go here, and 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 so on and so forth. Does that make sense?
Okay. Yeah, that makes sense. Like meaning like the outer shell electron moves, not the whole thing.
Exactly. Because the force from the magnet on this electron right there pulls it this way, leaving a hole, which this electron then fills, leaving a hole here, which this electron then fills, leaving a hole here, so on and so forth. Does that make sense?
Yes.
Okay. And you and I are engineers. We have the concept that electrons move. When you talk to a scientist who's been like actually trained, degree, and practicing scientist, they say the holes move. And you need to, whenever you interface with them, should you ever need to, you need to have that in the back of your brain that scientists say holes move and we as engineers say electrons move.
Okay.
And there's a very, very little chance that you will ever need that. But should you ever delve into like the biomedical world, that's where you need to have the concepts of you will be saying two different things meaning the same idea. So, yeah, we'll just leave that there. That's a whole nother like hour-long topic, but we'll just leave that there.
Okay.
All right. Let's move that back into place. Okay, so before I forget, so if I've got all the electrons on this end and I move this magnet away, do all my electrons stay on this end or they disperse again?
They just on the wire, meaning?
Yes.
They I'm gonna say they disperse again.
That's correct. And the reason for that is you've got a whole bunch of negative charge here and a whole bunch of positive charge here and no more force on them. So they're going to equal out. Okay. Does that make sense?
Yeah, like at the end of the day, they want to be either balanced or whatever they were to start. Is that a good way to look at it? Like, so for example, like this copper with this one valence electron at the very outer shell, like if it's not giving it up, it wants it. So once that thing moves, it's like it's going to get it back pretty much.
Exactly.
Like it's going to move back to it because it's like, hey, this is actually mine. So it's going to come back versus, hey, I'm going to give it to you because at the end of the day, I'd rather be balanced, so you take it. But if you're not going to take it, I'm going to take it back.
Precisely. If this is the very last copper atom in this wire here, it's not going to have, we'll assume it's not going to have a valence electron here. So it's going to have a slight positive charge, which means when the force of the magnet's removed, this valence electron is going to go, oh, I want to go to this positive charge. And it's going to neutral this out, and so on and so forth. This one's going to see a positive charge here and go there. This one's going to see a positive charge and go there, so on and so forth. It's literally the reverse. So exactly. Does that kind of help solidify your concern over that one?
Yeah.
Okay, cool. All right. This is basic math mixed in with a little bit of mechanical concepts. Okay, so electrically speaking, our base formula is voltage is equal to amps times resistance. You'll see this is E and V both. Okay, and the reason it's a kind of a swap up between two is what field you're in, especially if electrical people work with mechanical people frequently, it's going to be an E. because velocity is normally represented as a V, and we need to distinguish velocity versus voltage. So this can be an E or a V. Most mechanical people recognize force is equal to mass times acceleration. Like that's their base formula, just like this one's ours. And if you're a civil person, maybe the only one you recognize where mud is equal to dirt plus water. So. All right, so to keep going, to understand what this is, technically the amps is 1 coulomb of electrons per second. And a coulomb is equal to a ridiculous amount of electrons. So if I have that many electrons that flow through one set of, one location for 1 second, I have exactly 1 amp. Does that make sense?
Yes.
Okay, cool. All right, now to put this in water terms, which most people understand a little bit better, you can think of amps like your gallons per minute. How much gallons per minute is the time. It's, electrons per second, gallons per minute, right? And then your voltage is your pressure, which in this case is PSI, and then resistance is, it's still resistance, right? Because if you have a water hose that is 2 miles long and you turn the water on the faucet, 50 PSI at the faucet, you're not going to have 50 PSI at the end of the water hose. You will still have the volume of water, but you won't have the pressure of water. Does that make sense?
Yeah.
Okay, good. Just that's going to come into play here in a little bit, and you will have to remember that because I've got a small test for you as we go conceptually. Like I said, asking you questions. All right, so now I've got a loop of wire, right? One solid loop. I tied the ends together. Now when I move this magnet here, which way do the electrons flow?
To the right.
Right. What about on the bottom? Which way did they flow?
They flow to the left, I think.
There's a positive charge here. So
it'll still go right. Like the whole thing just goes to the right.
Exactly. Let me see if I can make this a little bit bigger. Cool. There we go. Oh, sorry, I didn't realize that was so small. All right, so yes, electrons still flow towards the positive side because both of these parts of the wire see that. And that's not what we want. We want them to flow in a circle. Right? So we're going to add a battery, right?
Okay.
This is essentially the pressure that we're adding. You can think of this as putting like an elevated storage tank or all right. So if I'm applying force on this little lever pushing water out, it's going to increase in pressure, right?
Mm-hmm.
That's essentially what this battery is. You're applying force to this. So knowing that this is the negative side of the battery and this is the positive side of the battery, which way are the electrons flowing? Top or bottom?
I would say negative to positive because the electrons want to flow to the positive. So the bottom one.
Negative.
Unless you're wanting to say it's going in a circle, like, oh, well, I guess I get what you're saying. Like it's gonna go clockwise because
Correct.
like the electrons are gonna go around the whole thing and then hit the positive. It's not like going from. Yeah.
You are correct, actually. If you have a negative side of the battery, which means you have a massive amount of electrons, negative electrons, right?
Mm-hmm.
So whenever you allow this to flow, meaning you close the circuit, it's going to all go from the negative side through the copper to the positive side. And whenever everything's equaled out, it's no longer going to flow and your battery's going to be dead.
Oh, so that's pretty much what happens when batteries die. There's just not enough negative going going through it, hence why it's neutral, and then it just, I don't know if I'm using like neutral properly, but it's gonna, there's gonna be no flow running through it. Is that correct?
Essentially, yes. It's very similar to, like, instead of H2O, you have electrons here. Well, when you run out of electrons here,
That's
this
it.
water's not going to flow anymore. It's it, right? You
Yeah.
either have to replenish the electrons, or we're going to skip that.
Hence, once you run out of pressure, there's no flow. Like you said, like the voltage is equal to like pressure, correct? That's what you said. So if in like mechanical speaking, like with water flowing, if there's no pressure, it's not flowing. Same goes with like electricity. If there's no voltage, it's not flowing. It's not flowing.
Exactly.
Okay.
Tracking that so far?
Yeah.
Okay. So yes, the electrons flow from the negative side clockwise to the positive side. All right. So first math problem. And I added a switch just because if you just connect this light bulb, there's no way to turn it on and off. And if you have no light bulb, the electrons are going to flow very, very quickly. If you have very low resistance, voltage divided by stupid low resistance equals very high current. Right? Z is equal to IR?
Yes.
Okay, so let's go back to that one right there. If I have, 0.0001 ohms of resistance, and I got 12 volts, 12 divided by 0.0001 is going to be a stupid amount of amps.
Because you have low resistance.
Yeah, for a very short amount of time, because I only have so many electrons I can push through.
Okay.
All right. So, hence the idea of you need a resistance or a load. Those two are interchangeable for now. A resistance and a load are interchangeable for now.
And hence why this is the same situation where the voltage is going, okay. So you're pretty much just wanting to know what the resistance is for this?
Yeah.
8
yep.
ohms.
Yes. And I know this is super simple and easy, but I'm using this simple math for a reason, for a future, like here in a few minutes. There we go. All right. So super simple, easy math, right?
Yes.
Okay. But we haven't actually described work, or in electrical terms, power. Okay. So watts, which is W, which I probably should actually put in there. Wattage, watts. There you go. Same thing. Okay. So wattage is known as what y'all call work, we call power. Conceptually the same, right?
Mm-hmm.
So if I have both voltage and amperage that a load is consuming, I know how much power, how much work it is required to, in this case, light that lamp.
Yeah.
Tracking so far?
Yeah.
Okay. I need to know both of those if I'm going to provide correct power to a load, to a lamp, a light bulb in this case. Because if I apply too much voltage, I'm going to blow the thing out. If I don't apply enough voltage, it's not going to actually turn on. Same concept with hydraulic transmissions or rams or motors, something like that. If I have something that I'm using hydraulic force to move, I have to have both the pressure and the volume correct.
Gotcha.
Does that make sense?
Yeah.
Okay. So next easy question. If I've got 28 volts on this battery and I'm using 56 watts of power, what are my amps and ohms?
You have 2 amps.
Yep.
And then 14 ohms. Yeah, because it's volts divided by amps to get the resistance. Yeah, 2 amps and 14 ohms.
Correct. Write that down before I forget. I didn't actually do the math. I ran out of time. You said 14, right? Okay.
I'm like writing stuff, but after we're done, you're gonna share this, right?
Yes, I will. I would
Okay.
totally share this. We're looking on time. We got 9 minutes left. Okay. But what if I have
Halfway
more
through.
than yeah? What if I have more than one load on there? In this case, more than 1 amp. How my voltage?
You
Okay.
mean more than one resistor?
Yes.
Okay. It depends because one's in series and one's in parallel. Ooh.
We'll stick with
Series
stick with
is R plus R is like the R plus R. Well, like R1 plus R2 equals R all. And then I know like the parallel is like 1 over R plus 1 over R, right?
yeah.
I'm like,
Close.
I'm trying to think. I'm like, I'm pretty sure that's how it works. Regardless, you still get the same amps. It just depends on your size of your resistors. The amperage is still going to be the same regardless of how you set up your resistors, correct?
I'm just gonna say yes for now.
Okay. I'm assuming
Again,
also, yeah.
glossing over things. So yes.
So if you have two,
Oh, you don't have to do the math. This is
I don't.
conceptual at this point. No. This is conceptual at this point. All right. So the question I have for you on this is, if I okay, you got that right. Okay, so on this super simple circuit, I've got a multimeter. Where would I put the test leads to test for voltage?
You're trying to test the voltage?
Yes, if I want to check what voltage this circuit has, where would I check it at? And there's 2 locations. Well, 3 technically, but we'll just stick with 2 for now.
Either side of the like negative and positive on the battery? Like stick one end on like there and one end there?
Okay. Yes.
And and you can also put it on the, this is a guess, the resistor, like on either side of the resistor.
The load. Yes. Assuming the switch is closed, yes, this is correct.
Okay.
Now, if the switch is open,
You have to put them, oh, if the switch is open, you have to put them on the resistor side, right? Because
so
there's right?
yeah, so if the switch is open, this is where you will read the voltage at, other side of the switch. Because you've got pressure here, but you've got an open in the circuit, which means you have no pressure here.
Gotcha. Okay.
It's like having a closed, an open switch is kind of equal to having a closed valve in the water world, right? If this valve's closed, you're going to have, pressure on the upstream side, but no pressure on the downstream side.
Gotcha. That makes sense. So that's how you'll be able to measure it.
Exactly. So yeah. So if this switch is open, doing here, you're going to read 0 volts no matter what you do.
If it's open. Okay.
Mm-hmm.
Which makes sense because it's on the it's on the downstream side of the switch.
Exactly. Downstream side of the valve. Yep. All right. So for amperage, if I wanted to measure how many amps was going through there, through this circuit, assuming the switch is closed, how would I do that?
On either side of the left one, on either side of the left one, on the very left.
The battery?
Yeah, on either side of the battery, if it's closed.
So the answer is none of the above, because I have to insert this multimeter into the circuit to figure out how many amps I have flowing through the circuit. So what that's going to look like is something like this. It's not what I wanted. So it'll be battery, we'll do it like this. Into the multimeter, out of the multimeter, and then you've got the load here, which I'm just going to draw a quick resistor all the way back to the battery. Since the electrons are flowing through this conductor, they have to flow through the multimeter and continue down. Does that make sense?
So no location because this is the way you would have to do it?
Yes.
Okay. That makes sense.
If you've ever seen a flow meter in any water or even HVAC, you have to actually stick the flow meter into the water.
Yeah, into the stream. Yeah, and because all of them, depending on how it measures it. Yeah, no, that makes sense. And you'd have to, it's pretty much having to do the same thing.
Mm-hmm.
Okay.
Exactly. Now, like I said, there's exceptions. I'm glossing over a ridiculous amount, but conceptually, this is the idea. And this will be modified before too long, but for now, you need to have the understanding that this is how it works.
So in the above where all the arrows, it's none of those locations. It's this.
So this is voltage, testing for voltage. Voltage testing. And this is current testing.
Gotcha.
Like I said, as we keep going, this base concept will not change, but there are additional ways to do this. But if you can wrap your head around this, this is a great start.
Okay.
And it is currently 8:30. Did you have any questions for me before I stopped?
I don't think so. So far, some of the stuff like I had learned about and either forgot or like it's just helping to understand like where we're going with it. Like, yeah, I learned it before, but I didn't know why I needed to learn it. I was just like, yeah, that's it. But now it's like connecting pieces of why it matters.
Nice. Yes. Yep.
Yeah, so
and this
far.
is, like I said, the base. Like this is step one. If you cannot wrap your head around this, then we need to review and keep going and keep explaining before we continue on with the additional lessons. So
Yeah, I think the most thing that the thing I'm having the hardest time probably wrapping my head around is the current testing, but everything else for the most part makes sense.
yep, and that's exactly why I put it in there. Literally, that's exactly why it took me quite a few years to wrap my head around that as well.
Like
Going back to this, if I needed to measure the flow of water, like I have to stick something in the water, right?
yeah.
And this is essentially sticking the multimeter into the flow of electrons, or in this case, water.
Gotcha. Like when you explain it that way, I get it, but just looking at the current testing without thinking of the other way, it's like I'm like it's like blank, like I don't know. But once you explain, like as long as I can remember, like think about it like a flow meter, I get it.
Yeah. Okay.
But the second I don't think about that, I'm like, what are we doing?
Which makes sense. I mean, I get it. And like I said, it took me quite a few years to get this one. So I'm going to go ahead and stop recording if you do not have any more questions.
Nope, no more questions.
Alrighty.